Hello, in this video let's discuss fourth question of today's contest. You are given an integer array nums. You want to maximize alternating sum of nums, which is defined as the value by adding elements at even indices and subtracting the elements at odd indices. That is v of 0 minus v of 1 plus v of 2 minus v of 3 and so on. You are also given two integer array swaps where swaps of I is p of I and q of I. For each pair p of I and the q of I in swaps, you are allowed to swap the elements at indices pi and qi. These swaps can be performed any number of times and in any order. Return the maximum possible alternating sum of nums. For example, given a vector 1 to 3 and the swaps are 0 to 1 2. By doing some operations, we can get the final array as 2 1 3. So the maximum value will be 2 minus 1 plus 3, which is 4. N is up to 105, values are up to 109, and the swap's length is also up to 105. So very simply, we have to find the maximum sum of alternating sums. V of 0 minus v of 1 plus v of 2 minus v of 3 and so on. Even indices minus odd indices value sums. For example, let's say we have swaps as 0 1, 0 3 and 1 2. So if we have something like this, then 0 1 can be swapped, 0 3 can be swapped, and 1 2 also can be swapped. So if these three are the swaps given, then we can swap any two. So we can swap 2 3 also. How? We can swap 2 1, 1 0, 0 3. So 2 3 will be swapped. We can swap 1 3 also. We can swap 1 0 and then 0 3. So finally, if these four are in a single component, then we can make sure that any two can be swapped. So simply we can try to construct a graph for every swaps so that if A, B are in a single component and B, C are in a component, indirectly A and C also will be same component, which means that A and C can be swapped using the given operations, like using the given values in swaps. So all should be in a single group. So you use a graph to store the component wise. And then very simply we can use DSU to track the components and ultimate parent, because the main goal is to find the unique component, because let's say we have 0 1 2 in same component, 3 4 in a component, and then find other component. So how can we differentiate between these three? So we can differentiate these three if we have some unique value for every component. If the unique value of all these three is 0, all these is 3, and of this is 5, then if we have three unique values, then we can say that we have three components, and in three components we can have these values individually. So we can use GSQ to track the components. So briefly, we can use the merge by size also. Let's say we have these two trees already connected, and now we have got a query to add 0 and 3. So if we have to add 0 and 3, there can be two ways. So parent of 0 can be made as 3, or parent of 3 can be made as parent of 0. So DSU is simply a data structure that merges the given edges in least time complexity, so that the ultimate parent node of every component can be found in of login. For example, let's say we have three queries, 1 2, 2 3, 1 4 and 5 6. Let's say we have four queries. So in these four queries, we have to do what we have to do. So we have to merge those both, and before merging, we have to find whether they are in the same component or not. So this is the question, what to do. So coming to 1 2. So initially all are in different nodes. So initially all are different. So now we have to merge 1 and 2. So if we are able, like if we are going to merge 1 and 2, we have to check whether they are already connected or not, right? So initially they are not connected. So initially no, because they are not connected. And now after the query, then we have to add 1 and 2. So we have to add edge between 1 and 2. So there is only one edge for now. So we can simply add an edge between 1 and 2. And now let's come to 1 3. So coming to 1 and 3, are 1 and 3 already connected? Are 1 and 3 already connected? No. So answer is no. And then we'll merge 1 and 3 also. So now 1 and 2 and 3. So even now we have to add 1 and 3. So let's assume that we are adding like this 1 and 3. And then next query is 2 and 3. So for 2 and 3, 2 and 3 are already connected. So the answer should be yes. But there is no direct edge between those. But indirectly they are connected. Why they are connected? Because it is connected to 1. So we can reach 1 from 2 and we can reach 3 from 1. So 2 and 3 are connected. So how can we get that 2 and 3 are already connected in of 1 or of log n? We ultimately want in less than of n, so that there will be no tailing. But we can do of n in DFS by or BFS. We can start from 3 and then we can do BFS or DFS to get whether 2 is wished or not. But we cannot do of n here because we only want in of log n. So how can we make sure that? So DSU gives this for away to find in off login. So while adding 1 and 2, we will make parent of these both as 1. This means that they both are in a single group. And we also made 1 3 as 1. We also made 1 3 connected. So parent of these both also will become 1. And now when we are trying to add edge between 2 and 3. The parent of this is 1 and the parent of 3 is also 1. So it means that they are connected. So simply by checking two values which are whether equal or not, we are able to get whether they are connected or not in off login. So this is why DSU is used. Even now, the main goal is to separate the components based on unique value so that we can process separately. So we are using DSU to get the components. And also coming to merging, we have two types. Let's say we have this in a component and we have this in other component. So how, let's say we got a query to add 0 and 3. So there are two ways, right? So parent of 0, this is also possible or this is also possible. But which is better? Both are ultimately same because indirectly we are making both them as equal. But which is better? It is better to add parent of 0 as 3. Why? Because this 3 is already big. So if we are trying to add this, then the height can be balanced. But if we are trying to reversely, but if we are trying to do parent of 3 as 0, for example, if we are trying to make this, then the height of whole tree is increasing. Because when the 3 is the ultimate parent node, then we can simply make parent of 0 is equal to 3, which balances the height. But here, when we are trying to make parent of 3 as 0, indirectly 0 is the main parent, but the height is increasing by 1 because this is the old height and this will be the new height. So indirectly, we are ultimately increasing time complexity, which is ultimately bad because both are either same. So we can consider the better one so that there will be more less complexity than what we think. So this is better than this because here the height is increasing so that the time complexity can be increased. And let's check this in the code for more clarity. And now we got different components. Now how to get the answer? Let's say we have three different components: 0 1 2. So 0 is connected to 1 and 2 and 3 is unique, 4 is unique. So there are no swaps that can be made with 3 and 4 independently. So now coming to first component. So in this component, what will be the final value? The final value will be v of 0 plus v of 2 minus v of 1 because it is sum of the values at even indices minus sum of values at odd indices. Here the only odd value is 1. So v of 0 plus v of 2 minus v of 1 is the maximum value that we can get. So think of signs only for now, not the value. So this will be the maximum value. And for this component, what will be the answer? For this, only minus v of 3 will be answered. Why? Because 3 is the only node in the component. So we cannot do any swap operations. So this is odd value. So finally, in the answer, it will contribute as minus v of 3. Because there are no operations possible. So this will be same as the initial. And what is the initial? It is odd index. So we'll get minus from this. So minus v of 3. And coming to 4, same plus v of 4 of this. Because we cannot swap this with any other. So initial value will be the final one, which is plus v of 4. And now let's start from 0. Let's start from 0 and think how to find the answer. So 0. So all the nodes 0 1 2 are in the same component. All the parent of these three is same. So all this will be stored in map of 0. So we are going to use a map to get the total number of nodes in that component with same parent so that we can traverse through that and we can find the answer. And now we got that these three are a single component. But how to find the maximum answer with respect to this component? So we already discussed that it is very easy. The only thing we want is the sum of values at even indices minus sum of values at odd indices. So we want the maximum value. So this should be maximum possible and this should be minimum possible. So let's say we have 0 1 2. So all these three can be swapped. So let's assume that value of 0 is 1, value of 1 is 2, value of 2 is 3. So after swapping, there are 6 type of arrays finally possible because we can swap every 2. So there are ultimately 6 permutations. So 1 2 3 1 3 2 2 1 3 2 3 1 3 1 2 and 3 2 1. So these 6 are possible. But we will select which one? So we will select one such that it will give the maximum sum of even indices minus odd indices. So it should be maximum of v of 0 plus v of 2 minus v of 1. So when is this possible? When this will give the maximum value? This will give the maximum value when we are taking the maximum values in the whole array as even values. For example, let's say we have 1 to 3. So if we have 1 to 3, we got that we will add two values and we will subtract one value. So which two we will add? We will add the maximum values. Which we will subtract the minimum one to get the maximum answer. So simply 2 plus 3 minus 1. These two are the maximum and 1 is the minimum. So why 1 here? Because there is only one index with odd index, which is ultimately getting subtracted to the final answer. So simply we will get the whole nodes in the component. We will count the number of odd and number of even, and then we so ultimately it is like even minus odd. So how to find the maximum? So we will sort the values based on the nodes in the group, and then we will select the first e maximum values. So we'll add all these v of 0, v of 1 plus v of 2 and so on till v of 0, v of e minus we will add the rest of all because the net sum even is added here. So we have to subtract odd also, which will be next. So in this way we can very simply find the answer. So for 1 to 3, what will be answer? It will be 2 plus 3 minus 1 because 2 even. So we have to add 2. So which 2 we will add? We will add maximum 2. So 2 plus 3 and the rest is 1. So we'll subtract that. So 2 plus 3 minus 1 is the answer. And now, so 0 is done. So the answer with respect to 0 is done. So now we have to come to 1 because we have to traverse all the components. So we have to come to 1. But 1 is already completed in 0, 1, 2 because 1 is already a part of 0 component. So how to make this correctly? Because we came through 0, we completed the traversal for 0 component. But now coming to 1, we have to do the same operation. But 1 is already completed. So how to make sure that there are no repetitions and every component is traversed individually only once? So why complicating things? So simply traverse the map itself which we stored. So let's say we have 4 components. So we have 4 components and don't think node wise. So start from component wise. So firstly start this and then so find the number of odd, number of even, find the maximum answer with respect to this and then come to this component. Find the odd, even, count answer for this and so on. So in this way we can add the answer for all the components which will give the final answer. So now it is very simple. So we'll come component wise. So coming to 0, the parent can be anything. So now this is also possible. The parent of 1 is 0, 1, 0, 1 to this is also possible. 2 can be 0, 1 to this is also possible. So now the main thing we are relaxing with respect to traversing component wise is the parent. For example, if let's say we are trying to store something like this 0, 0, 1, 2. So here there may be a complexity that how we should process the components individually. Because if let's say we completed 0, 1 traversal and now we came to 1. So if we came to 1, we have to know that it is already computed. The component 1 is already done so that there is no need to find this. So there is unnecessary complexity here because we have to find the answer for all the nodes. So we'll start from 0, we will come from 1. But when we reach 1, we have to know that it is already completed in some other previous component. So this is adding some other difficulty. So instead of this, we can just simply use DSU to find the parent. And the parent can be anything. The parent of 0, 1, 2 can be ultimately 0. They can be ultimately 1. They can be ultimately 2. So that is not a problem. So after storing, we can simply traverse parent wise and then this will simplify our answer. So hope you understand this. Let's check the code. So size and parent. Parent is the vector that stores parent of node I and size is the size of node I rooted at that node. That is useful to decrease the complexity to overlog it. So initially size of every component is 1, so make it 1 and parent of every node is that node itself, so parent of is equal to I. And then start traversing size swaps and then merge those both. And in merge what we are doing? In merge we are finding the parents. So we find the parents. If the both parents are already equal, it means that they are already connected. So simply return. Else, if the size of parent A is more. So let's say this is parent A, this is parent B. So if this is the case, then how we will merge? So we will merge such that the parent of PB is equal to parent of A. So parent of PB is equal to parent of A. The size will be sum of both because this is rooted at this. So size of this will be increased. So size of parent A is equal to size of parent A plus size of parent B and so on. And now we will use component and then we will traverse all the nodes and then we will try to separate best the components. So component of node dot pushback I and then go through component wise and then find the number of odd and even and then push the value of that into vals and then reversely sort. So long is equal to 0 and then get the highest maximum e values, because e values are getting added. So 0 to e, so add to that, and e to rest, subtract to the answer, and then simply add to the answer, return the answer. If you have any doubts, comment below. See you in the next video.